Hello everybody, this is Past Paper Guy. Today I am going to be taking you through the solutions of the AQA 2021 Assessment Materials. Now this is the first set of assessment materials called Mechanics and Materials and Further Mechanics. Now I'll provide a link below in the description, and this video will go on air as soon as this material becomes available to the public. Now, due to copyright restrictions, I'm not going to actually project the paper or the questions themselves, so you'll need to follow along by following the link and printing off your own copy. I'm just going to do the solutions to them. So here goes. So the first question, called question 4, which comes from the June 2020 paper, is a question about speed and motion. So it's got a graph of a velocity against time graph, and the first thing we want to do is it wants you to work out the average velocity of this. So the easiest way to do this is to break it up into 3 chunks and work out the area underneath each of the 3 chunks. So to do that, we use a pen. We need to remember that the axis down here is in minutes. So to do that, we have 1.5 minutes, so that's going to be 90 seconds, times by the average of these 2 values here, which is 15 plus 24 divided by 2, plus, and then section B, which is 1 minute, so that's 60 seconds, times by the average of these 2, which is just 24, plus, and then the area of this one, which is 1.5 minutes again, so that's 90 seconds, times by the average of these, which is 24 plus 12 divided by 2. So then we need to work all this out here, and we have 90 times by 15 plus 24 divided by 2 plus 60 times by 24 plus 90, and that's 18, isn't it? Times by 18 gives you 4,815 meters. And we divide that by 4 minutes, which is 240 seconds, to get, so speed is equal to 4,815 divided by 240, so that's 20.0625 meters per second. And then we have to compare that to the speed limit of 22 meters per second, so that's under the speed limit. So you'd write under the limit of 22 meters per second. Make sure that you make the final comparison. So the next part is about chevrons between cars on a motorway, and we're asked to suggest the distance between the 2 chevrons. Well, we're told that it could be reaction time could be between 1.6 and 2.0 seconds. So what we want to do is we want to take the worst case scenario, and that is 2.0 seconds. So the worst one is that it's on the longer of the 2 limits. And then we can do just displacement is equal to velocity times by time, because acceleration is 0. So it's just going to be 31 times by 2 is equal to 62 meters. Now, at this point, when I did this first time, I thought, right, so I'll suggest something bigger than 62 meters. So I suggested 70 meters because that was bigger than 62 meters, but they don't want that. They just want you to suggest exactly 62 meters. They don't seem to allow you to do anything else. So make sure that you don't round this or anything. So suggest that the distance between the chevrons is 62 meters. .3. So this is a SUVAT calculation. We're trying to work out how long it takes to stop and what distance you cover when you stop. So because it's a SUVAT, write SUVAT down here like so. We don't know the distance, we're trying to find that out. We don't know the time, we're trying to find that out. The initial velocity is 31, the final velocity is 0. We need another piece of information, so we need the acceleration. So we use Newton's second law, so Newton 2. So we have F equals ma, A equals F divided by m, which is equal to the force. The average braking force of the car is 6,800, 6.8 kilonewtons, so that's 6,800 newtons, divided by the mass of the car, which is 1,200 kilograms. So we have 6,800 divided by 1,200 gives us 5.666. It's negative because it's slowing down. 5.666 dot 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 there. And so now we need to find this one and this one. You can do it in any order. I thought the easiest one to work out was the time first. So I used A is equal to V minus U over T. So T is equal to V minus U over A, which is equal to V is 0 minus 5.666, etc., divided by, U is 31, and then that's divided by minus 5.666 dot dot dot. So we need to do 31 divided by our previous answer gives us 5.47. So that's going to be 5.47 seconds, rounds to 5.5. And we also can use the displacement is equal to the average speed, V plus U over 2, times by the time. You can use any of the other equations as well that you've got the stuff for, which is everything now, so you can use any of the other equations. So that's 31 divided by 2, I just thought this one was easier, times by our time, which is 5.47, which gives us, that's the number there. We need to times that by 31 halved is 15.5, isn't it? So that's equal to 84.794. So the answers are time is equal to 5.5 seconds to 2SF, and displacement distance is equal to, that rounds to 85 meters to 2SF. So question 4.4. So the question is, why does the chevron spacing not take into account the distance travelled as the cars are braking, but it does take into account the thinking distance, the distance between cars that you would travel as you're thinking about putting the brakes on? Well, the answer to this is really because the vehicle in front won't stop immediately. It will travel a distance during its braking period as well, which will be very similar to the distance that you travel, or the second car travels in its braking period. So the difference between the distances will be, if this is the car in front and this is the car behind, when this one's lights go on to say that it's braking, it starts braking here. The second car is going to travel to here when it starts braking. And when it starts braking here, then this car will have already moved on out of the way. So you need to make sure they start braking at the same place in order that they can come to rest roughly in the same place over here. So we only need the cars to be the thinking distance apart, not the combined braking distance and thinking distance. Right, explaining that for 1 mark's really, really tricky. So let's just give it a go. So the vehicle in front will not stop instantly. So it will continue to travel when it applies its brakes. Okay. The vehicle behind, therefore, must start to brake when it reaches the place the vehicle in front started to brake. Okay, I mean this is quite a lot for 1 mark that I'm writing here. You probably don't need this, but better to be safe than sorry. So the upshot of this is that the distance between the vehicles when this one starts to brake must be the thinking distance. So the vehicle behind must start the thinking distance behind the vehicle in front. Okay, I think that's probably over the top for the question. However, it's actually quite a complicated question for 1 mark. What exactly do they want for the 1 mark? That answers it thoroughly. I don't see how you can have a problem with that. Question 4.5. We have an embanked motorway, and the idea is that the frictional force is 0. So we've got a normal reaction there. We're at, what is it, 5 degrees, 5.0 degrees there. We have the weight of the object there, and it's going around in a big circle like that with a radius of 200 meters. Okay, so there is no force, there's no frictional force here or here, neither of those exist. It says that that's supposed to be 0. So we've only got the 2 forces acting on the vehicle. And what's going to happen then is you need this component here and that component. So that's the vertical component of N, that's the horizontal component of N. The vertical component of N must equal the weight, and the horizontal component of N is the resultant force which causes the centripetal acceleration. So let's write some equations of motion. Let's use Newton's first law to balance these. So NV has got to equal W, but NV is N cos 5 is equal to W. We also know that NH, so that's NV, NH is equal to N sine 5, and that's got to equal the centripetal acceleration, which I'm just going to call FC for the moment. Right, I'm now going to divide these equations by each other. So if this is equation 1 and this is equation 2, I do equation 1 divided by equation 2, and I get, well, the n's cancel. Sine over cos is tan. Tan 5 is equal to FC divided by W, like so. But FC is equal to, by definition, mv squared over r, and so that's got to equal W tan 5. Now we know everything. we're trying to find V. We know that, we know that, and we know that. So we can now rearrange and solve for V. So we get V squared is equal to R over M. W is mg. So the masses of the vehicle cancel, doesn't matter what it is. And then tan of 5. So here goes. We've got 200 times by 9.81 times by tan 5 is equal to that. So V squared is equal to 171.65 dot dot dot. So we need to square root that. And we get V is equal to 13.1 meters per second. So that's 13 meters per second to 2 significant figures. And that's the answer to 4.5. The next question 4. This one is from June 2019. And it's this trebuchet one with the sort of funny catapult thing. And the first thing is the catapult is designed so that the weight of the beam and the weight of the empty wooden box have no effect on the tension of the rope. Suggest how the pivot achieves this. So the idea here is that we've got a pivot in the middle and we've got a box and a thing there. And this one has to balance this one. So the way you get that is by putting this at the center of mass. So the pivot is at the center of mass of the beam and bucket. Right, it's 2 marks, so that's never going to get you 2 marks. So the clockwise moment balances the anti-clockwise moment. So that's the clockwise moment of the bucket balances the anti-clockwise moment of the beam, like so. 4.1, sorry. Right, 4.2. We've added some stuff here and we've got a rope here. So we can ignore the beam because that's already balanced. We've got a rope here at 50 degrees, like so, and we've got a force here, which it says is 250 newtons. That has a force of tension there. And here we have a force, well, this is 610 kilograms, so that's 610 G, like so. This is a moments problem. The easiest way to do this is to do it all in one go. So using the principle of moments, always write down what rule that you're using. So we want the clockwise is equal to the anti-clockwise moment. So let's go, sorry, anti-clockwise equals clockwise. So let's do this one first. That distance there is 4 meters. That distance there is 1.5 meters. So we've got 250 times by 4 is equal to t, oh sorry, no, got to add this one in as well, plus t, now we've got to resolve that so it's 90 degrees, so we're turning through 40 degrees, so it's cos 40, t cos 40, like that, and then we've got to times that by the distance as well, which is 4 meters, is equal to this one, which is 610 G, times by its distance back to the pivot, is 1.5. Right, so now we need to solve that for t. So we have t is equal, that's 1,000, so 610 times by 9.81 times by 1.5, take away 1,000, moving that over there, and then dividing that all by 4 times by cos of 40. Okay, so that's, you could do this in smaller steps. I'm just going to do it all in one go. So we get that for this part here. We take away the 1,000, to get that, we divide by brackets 4 times by cos of 40. Let's check them in degrees. Yes, I am. And we get that. So T is equal to 2,603 newtons, or 2,600 newtons to 2SF. 4.3 now. This is a standard range calculation. So we're going to use SUVAT twice. And to use the SUVAT twice, we're going to do it horizontally and vertically. The vertical one is going to give us the time, and we're going to use that horizontally to get the final range. So that's just 18 meters per second in both of those. There's no acceleration in the horizontal, and that's what we're trying to find out, is the range. In the vertical, we've got it's going down by 7.5 meters. Doesn't matter if you make that plus or minus, as long as you're consistent with your acceleration. The initial velocity is 0. We don't care about the final velocity. We do care about the acceleration. That's minus 9.81, as the arm's like this, and it sort of goes like that, doesn't it? And that's the range there. And that there is 7.5 meters, like so. And so we're going to work out the time using the vertical. So vertical to find flight time. Okay, so S is equal to UT plus a half AT squared. Minus 7.5 is equal to UT, is going to be 0 because U is 0, plus a half times by minus 9.81 times by T squared. So T squared is equal to 7.5 times by 2 divided by 9.81. So let's try that. 7.5 times by the 2 divided by this 9.81. My minus there and my minus there cancel, giving me a positive time, which is always good. T squared is equal to 1.529. Don't forget to square root the answer to get T is equal to 1.2365 dot dot dot. So that goes in there, 1.2365, which is the same over here. And then we use the horizontal to find the range, and we can use the same equation, S equals UT plus a half AT squared, but this time A is 0. It's not just that A is a dash, A is actually 0. So that's all 0. So S is equal to the time, 1.2365 times by the speed, which is 18, giving us 22.25 meters. So that's 22 meters to 2SF. Question 6.1. This one is taken from the June 2018 paper 1. So state the quantity that is not conserved during an inelastic collision. Well, I think they want kinetic energy here. And you've got to put kinetic, obviously, because energy is always conserved. Kinetic energy. 6.2. Right, so we've got these trucks and they're colliding, and we need to find out what the speed of the joined trucks, so they collide, they're coming towards each other, bang, they collide, and they move off in one of the other two directions. I'm going to guess they're moving to the right, but we'll find out. So we have, this is our initial, and this is moving this way with 2.8 meters per second, and this is 1,000 kilograms. And this truck here is moving this meters per second. So in other words, it's moving, another way of thinking about it, it's moving that way with minus 3.1 meters per second. And this one is 12,000 kilograms. And then together they move off, we'll say they move this direction, but the maths will tell us which direction they move, depending on whether it's plus or minus. And that's 28,000 kilograms with a speed of v. So we're going to use conservation of momentum. Again, write down the rule that you're using. And we've got 2.8 times by 16,000 plus, and this one has minus 3.1, that's taking into account its direction, remember, times by that must equal 28,000 times by v. Okay, let's work this out. So we've got 2.8 times by 16,000, take away 3.1 times by 12,000, and it is positive, so it is going to go to the right. So v is equal to 7600 divided by 28,000, which is the combined masses, which is v is equal to 0.27, and the rest of the things, but 2SF, and it's to the right. Okay, because it's positive, and we said that to the right was positive at the beginning, because that was positive. I put minus for that in, that comes out as positive, so that means it's to the right. Calculate the impulse that acts on each truck during the collision. Okay, so if we calculate one, it should be the same as the second one. So this is an opportunity to actually check our answer. So the impulse is the change in momentum. So we just need to work out the momentum before and after. So we'll do truck A. So truck A, the change in momentum is 2.8, its velocity, take away the final velocity, that's the change in velocity, times by its mass. So it's the change in velocity times by its mass, because its mass isn't changing. So 2.8, take away answer, and then we need to times that by that, and that is equal to 40457, which 2SF is 40000 2SF, and the units for a impulse we usually would write Newton seconds, but you probably be all right with kilogram meter per second there as well. Right, as I said, we can check our answer. So this one here, truck B, so the change in velocity here is the final value, which is 0.27. Take away the start value, well the start value, remember, is negative, so 3.1 times by 12,000. I actually got these numbers the other way around, it should come out as a minus number, but it doesn't matter because it's only asking for the size of it. So we've got 0.27, take away 3.1 times by 12,000. Hopefully that's the exact same, yeah. Give or take a rounding error, that's the same. So that one checks that we got the right answer. So 6.4, in this one we need to explain how this would be different if the collision was totally elastic. Well, if it's a totally elastic collision, they're not going to stick together, they're going to bounce off one another. And which direction they end up going depends upon the masses and their initial speeds. But it says not to do any calculations, so we sort of need to figure out what's going to happen. Well, it's likely that they're going to come in like this and then they're going to bounce off each other and go back in opposite directions. We can't know that for sure. This one might be so much that they bounce and that one goes off faster, but that one still keeps going. So it doesn't necessarily mean that they have to go in opposite directions, but the answer in this case is that they do. So let's stick with that rather than... I could talk about this question for 20 minutes, but it wouldn't help you do this assessment, would it? So let's just get on with it. Right, so the trucks will collide and rebound off each other. So A to the left and B to the right. Now the only thing that you do know in a completely elastic collision is that the difference in the speeds before must equal the same as the difference in the speeds afterwards. Now if they are exact same mass, then they would come in and they would exactly exchange their momentum. But that doesn't happen here, although the mark scheme would allow you to say that if you said that the momentum of B is transferred to A and the momentum of A is transferred to B, the mark scheme on the paper says that that's okay, but it's not true. I'm going to think of a different way to explain it, which is true. Okay, so if we think about the relative speeds afterwards, this one is now going to be bouncing off that way, and this one is going to be bouncing off that way. Now, this combined momentum has to equal this combined momentum. This combined momentum was in the right direction, so this combined momentum is going to be in the right direction, which means that the momentum of B will be bigger than the momentum of A. So B will move faster than A because, well, there's two reasons. It's got more momentum than A. It has more momentum than A, as originally the total momentum was to the right. So the momentum of B has to be bigger than the momentum of A. And the second reason that B will move faster is because it has a smaller mass. B also has a smaller mass, so will move faster than A. Okay, even if they had the exact same momentum, which they don't, B is going to end up with more momentum than A. Even if A was still travelling in that direction after the collision, that all of that would still be true, because this would have lost some momentum and given this one even more, so this one would still be going faster than A. So that's true. The next question is question 5, which is taken from June 19 paper. And the first thing that we want to do is to find the kinetic energy of a vehicle, and it's a show that question, so we've got to show all of our working. So we need to convert this in kilometers per hour into meters per second. So we times by number of meters, divide by number of seconds, and that is 30.55 ... meters per second. So that's the first thing we need to do. Then we need to work out its kinetic energy. That's equal to a half mv squared, equal to a half times by the mass is 1,500 times by v squared, which is that, so 30.55 squared. So we square that, and then we times that by 1,500 times by 0.5. Oops. 0.5. So let's try this again. 30.555 squared times by 1,500 times by and a half gives us 700.228 joules. Remember to write down all your decimal places because it's a show that question, which is approximately equal to 700 kilojoules which is what they want. Right now, this vehicle is going to crash into a barricade. So we want to, so that's its original velocity there. That's its velocity in the length of the road, 20 degrees there. That's its velocity perpendicular to the barricade. And it loses all of this velocity and keeps this velocity here. So what are we supposed to do? We're supposed to calculate the component of momentum of the test vehicle in a direction along the safety barrier. So we want to find, you can either find the momentum here and then find its component, or you can find the velocity here, the component of the velocity first, and then find the momentum. So I'm going to find the component of the velocity first because it's going to be useful later anyway. So the component of velocity VL parallel to the barrier, that's going to equal V cos 20, which is, or V was, what was it, 30 point, lots of fives, and then times by cos of 20 gives you 28.71 meters per second. Right, so the momentum is going to equal mass times velocity. And it's just this component of it, so that's going to be just that speed times by the, that's the velocity times by the mass, which was that, wasn't it? So we're just going to times this by 500, nope, by 1,500, so we need to times it by 3 again. And so we get MVL is equal to 43,069. So that's 43,000 to 2SF, and the units are kilogram meters second minus 1. Okay, now we need to show that the kinetic energy that's lost is about 80 kilojoules. So the way to do this is just to work out what the final kinetic energy is. So this is 5.3. So final KE, well, all of that velocity is removed. That velocity is the only bit that keeps going, so that's why it's useful to have this now, is equal to a half mvl squared, which is equal to a half times by 1,500 times by 28.71 squared. So 28.71 squared times by 1,500 times by 0.5 is equal to 618,198, and then delta KE, the change in kinetic energy, is equal to the final minus the start, is equal to 618,198. Take away this 700,228, and that is, it's negative, so we've lost kinetic energy, which is what we'd expect. And that's how much we have. And again, it's a show that question, so make sure that you include more decimal places than you need. The next question, there are lots of ways to do this, but this is by far the easiest way, is just to do a work done. So the work done by the barrier is going to be this. It's going to be the force times by the distance. So the work done by the barrier, well, it's actually the maximum work done by the barrier, is going to be force times by distance, and it can exert a force of 60,000 newtons, and it can exert that over a distance of 1.5 meters before it snaps. So that's going to equal 90,000 joules. So that's the maximum work done by the barrier. The amount of work that needed to be done was only 80,000 joules. 90,000 is bigger than 80,000, so the barrier can hold. Okay. Question 21, we're into the multi-choice questions now. This one is from paper 2020, so you won't have this, but it should be on the AQA website anyway. So we've got a tap dripping and we've got one drip that hits the ground and the next drip left afterwards and is there, and we need to figure out how far this one has fallen by the time this one hits the ground. So the first thing to do is to figure out how long it takes this one to hit the ground. So we're going to need S is equal to UT plus a half AT squared. This will tell us how long it takes the first drop to hit the ground. So S is 0.80, U is 0, plus a half. So this is, I've put this as a positive number, so my 9.81 will be a positive number as well, T squared. So we've got 0.8 times by 2 divided by 9.81 is equal to that, and we need to square root that, and we get 0.4 seconds. So T is equal to 0.403 ... seconds. Okay, it's multi-choice, so you don't have to show all this working. Right, so if that's taken 0.4 seconds, then this one left 0.2 seconds after this one, so this one's travel time is 0.2 seconds less than that one. So drop 2 will have T is equal to 0.2038. It's half that, but don't fall into the trap that means it's gone half the distance. It hasn't, because it travels the second half on average faster than the first half of the time. So now we need to use S equals UT plus a half AT squared again. So this time S is equal to that 0 again, plus, and then we've got a half times by 9.81 times by, and then our new time, which is 0.2038 squared. So we square that times by 9.81 divided by 2, which gives us 0.2 meters, which is answer B. Question 22, this one's also from paper 2020. Now, you can't use energy on this equation, you have to use momentum. And the reason you can't use energy is because it's an inelastic collision. So it's going to give you a very, it's just not going to work properly. So we want to use momentum to start with. So we have the pellet being fired at the block, and it goes up 200 meters per second, and it has a mass of 5. And then the block and the pellet both move up with a velocity of v, and they have a mass of 100 grams when they're put together, because that's 95 grams there. So this has no initial momentum, so we just do 5 times by 200, that's the momentum before, must equal 100 times by v, so that's just v is equal to 10 meters per second. Right, so we know that the block is moving up at 10 meters per second to start with, but that's not what we're after. We're after the height that it can reach, so we need to use some suvat. V squared is equal to u squared plus 2as. So v squared is 0, that's the final velocity when it gets to the highest point. U squared will be 10 squared plus 2 times by, the acceleration will be downwards, so it'll be in the opposite direction to u, so it's negative 9.81. But you could use 10 here, and then you get the answer because it's only multi-choice, times by s. So that's minus 100 divided by 2 times by 9.81, so that's 100 divided by 20 is equal to s, so that's about equal to 5 meters, which is answer A. Okay. Question 23, this is also from 2020 paper 1, and the power out will equal the work done, which is the weight of the object times by the height you move it through, work done is force times by distance, divided by the time. The power in is going to equal the power developed by the motor. The efficiency, therefore, is going to be the power out divided by the power in, or the useful power out divided by the total power in. So it's going to be equal WH divided by T times by 1 over IV. So we were looking for WH over ITV, which is A. Question 6, this one comes from the same paper. Mechanical power, well, that's just a basic units one, is kilograms meters squared second minus 3, which is answer C. You know that because power is equal to energy divided by time. An equation for energy would be a half mv squared, which is a kilogram meter squared over second squared. You've got to divide by an extra time here, so you get an extra second on there, so you get a kilogram, you got meter squared from there, and you got 3 seconds there, so minus 3 there. It's from June 2019. Object of mass is m is moving the circle radius r. It completes n revolutions every second once its kinetic energy. So I did this first this way. Omega is equal to 2 pi n. That's the angular frequency. That's 1 revolution in angle, and that's how many it's doing a second. Its moment of inertia is equal to mr squared. So the kinetic energy is equal to a half I omega squared, which is equal to a half times by mr squared times by omega squared, which is 4 pi squared n squared. So that cancels with that to leave a 2, which is answer C. Now, if you haven't done the option, engineering option, you can just do it this way instead. You can go the distance around the circle is 2 pi r, so the speed is equal to 2 pi r times by n every second. So that's the linear speed of it, and then you can go a half mv squared, which is equal to a half times by m times by all of this squared, so that's 4 pi squared r squared n squared, and that cancels with that to make a 2, and lo and behold you get the exact same answer. Question 19, this one's from 2019 as well. We've got 50 newtons spread out over 1 millimeter square, and we need to find out what the pressure is, or the stress on the wire. Now, it's just an estimations one. Now we've got to convert this into meters squared if we're going to find it in pascals. So 1 millimeter square is equal to 1 times by 10 to the minus 3. That's to change it to millimeters, but we're squaring it, so that's squared. So that's 1 times 10 to the minus 6 meters squared. So it's 50 divided by 10 to the minus 6, which is equal to 50 times 10 to the 6, which is between 10 to the 6 and 10 to the 9. So it's going to be answer is C. And that is the first of the AQA Assessment Materials 2021. I'll be posting the rest as we go along.